All right, good afternoon, everyone. Welcome to the webinar. We're going to be talking about pavement distresses today. So we will go ahead and get started. A little bit of housekeeping. I know a lot of you have attended other webinars and are familiar with the controls, but just in case you are new to us, you do have a control panel that will expand and collapse with the little orange box. You have a mute button. However, all of you for this webinar are in lesson only mode. You can toggle back and forth between full screen and not full screen. When you are not in full screen, you can zoom in and out and kind of adjust your screen for what works best for your visibility on your device. There are some audio tips there. You have a phone in option if anything goes wrong with the computer audio. There is also a questions pod, and I would encourage you to use that at any time to ask questions that you have as we go along. We will be stopping to answer those questions periodically. And then I would also point your attention to the handouts. You do have a handout for this webinar, and it is the presentation that I'm going to be giving. So you can click on that and download it at any time during the webinar. My name is Stacy Williams. I will be your instructor today. I'm the director of the Center for Training Transportation Professionals and work a lot with the Arkansas LTAP program. For the webinar today, you will be getting 2 hours of Road Scholar credit, and you will get a certificate for that. Those will be emailed out probably next week. And I know that a lot of those who are registered for today are attending as a group. So if you would send me an email with the listing of the folks who are attending, and that way I can make sure that everyone who is in attendance will get a certificate. Also, we have Tally Faulkner online with us today. He'll be handling all of the IT issues and watching the questions pod and all those sorts of things. So if you have any technical issues during that, he will be the one to help us out. All right, I'm going to start out with a poll question real quick. So I should launch that, and it should be showing up on your screen right now. And what I would like to know is, what method does your agency use for pavement distress data collection? You should be able to select multiple answers. I'm going to give you a few more seconds to answer that. Our choices are manual surveys, automated data collection, visual surveys, my agency doesn't collect this data, or I don't know. And it looks like most of you have your answers in. I'm going to go ahead and close that poll. And the responses should show on your screen now. We've got a few of you that do manual surveys and automated collections, a few more of you who do visual surveys, a pretty good chunk of you who do not yet collect this data, and a few that don't know. So very good. I'll close that and go back to the presentation now. All right, so we are going to be talking about pavement distresses and what to look for. And as we know, when a new pavement is built, it's in great condition, or should be in great condition. And over time, that pavement is going to deteriorate to some extent. And so there are a number of factors that contribute to that. One being the load on the pavement. So we put traffic on top of the pavement, so that's a weight that pushes down on it. And so we're also dependent then on the support from underneath the pavement that has to hold it up and carry that traffic load as well. And then we have environmental conditions that definitely play a big part in how long that pavement is going to last and what distresses show up. So the first thing that they will tell you in any pavement design class is the most important feature of a pavement design is drainage, drainage, and drainage. And so I know some of you have heard me say that many times before, but drainage is probably the single most important factor in the longevity of a pavement, because water and pavements just are not friends. They don't mix. they don't do well together. So you can see in the picture the types of distresses that we see. When we have a lot of water in that area, it softens the subgrade. It gets into those small spaces within the pavement structure, and we don't want that. So it causes a lot of deterioration. So the first step in trying to combat those sorts of distresses is to deal with the drainage. If you have any type of distresses that you're trying to mitigate or repair, doing some type of corrective maintenance, if you don't first correct that drainage issue, you will see those distresses come back over time. So when a pavement has any type of an opening in the surface, the water is going to get into those cracks. And you can tell in this picture, all of the cracks are highlighted really well. It's after a rain, but the crack areas are still kind of damp or darker looking from being wet. So right after a rain is a great time to go out and look at your pavements because it's easier to find those cracks and those openings where water is getting in. Now, our pavement failure mechanisms, for the most part, asphalt is going to just either crack or rut. We will also be talking today about concrete pavements, and concrete pavements crack. So those will be the main things that we're looking at. You can see in the picture for the asphalt that we have both cracking and rutting in the same area. Now, a pavement, like I said, when it's new, it should be in very good condition. And over time, that condition is going to deteriorate. So if we were to plot that on a graph, we would start out at the beginning of the pavement's life with a very good condition, and then that condition level is going to go down. But it's really not a straight line like what we see in this picture. So we're going to change that a little bit. We see that early in the pavement's life, it kind of rocks along and does really well for a bit. And then there's some deterioration. We drop down into the fair condition. And then maybe when we get into that fair or critical condition, the slope of that line gets much steeper. So we kind of fall off the cliff, so to speak. So what that tells us is that when we look at the speed of deterioration, we can kind of be lulled into a false sense of security in that a new pavement does not deteriorate that fast. But once we start to see those distresses, they will kind of snowball on us and they'll get worse a lot more quickly. So then we drop from that critical down into poor condition a little faster. Now, every roadway is different, so we may have some that last a little bit longer. We may have some that don't last quite as long. And we're going to have to consider some major factors. If we have changes in our traffic levels, or if we have some really extreme weather conditions that year, that's definitely going to play a factor also. So somewhere in this range, we can probably chart out what our typical pavements look like. Now, one of the things about a lot of the pavement management information that you might find, we kind of have to think of things in categories because we have high traffic roadways, low traffic roadways, and for local agencies in particular, you have a huge variety in the types of pavements and the types of traffic levels that you see. And so your band of deterioration may be much wider. So you might want to put those roadways into categories to say these types of roadways have a minimal slope. These types of roadways tend to deteriorate more quickly because they do have more traffic. So looking at what you have, put it in categories that make sense, but we will see a range, and the more variety of roadway type that you have, the larger that range will actually be. So if we were to collect data, which is what we are hoping to get to, we're going to start charting that and plotting those values of what condition we have, and we'll see that over time the condition does drop, and we can collect that for a number of roadways and then kind of put that all together, and over time we're going to get a better sense of how quickly things change and when is the best time to do those corrective maintenance activities. Now, if I do some corrective maintenance, you see the little stars represent the level of the condition, so to speak. So When you see the green arrow that sticks up, that represents doing some type of corrective maintenance and then bringing that condition back up to a higher level. The green arrow also kind of represents how much it's going to cost to do that. So if we wait until a later date or a longer time, we're going to see that adding something after we've waited for that condition to drop to a pretty crummy level, it's going to take a lot more money. It's going to take a lot more effort to bring that back up to good condition. And then it will kind of start over on its curve. Usually a curve for a rehabilitated pavement or a maintained pavement, probably not quite as long of a curve as what we see for the newly constructed ones, but it does depend on the type of treatment that we apply. All right, first we're going to look at asphalt distress measurements. So we need to think about how asphalt works, how it fails, and how we need to think about all these different distresses. So asphalt pavements are flexible pavements. They're made to be that way. They're made of rocks and oil, and that oil is the glue that sticks it together, but it's a very viscoelastic material, so it has some give to it. In the summertime, when the weather is hot, it has a little more give. In the wintertime, it tends to get more stiff, a little more brittle. And so we need to balance those two things, because if we have too much flexibility, we're going to get rutting. If we have not enough flexibility, then we're going to end up with cracking. When we put a load on the pavement surface, represented by the tire in this picture, that load presses downward. So throughout the thickness of the pavement, we see compression at the top of the asphalt layer, but at the bottom of the layer, it tends to pull apart. So if you're bending, say you have a piece of styrofoam that's pretty thick and you want to break that, you bend it, it compresses at the top, it pulls apart at the bottom, and that's how you're able to break that apart. The same thing happens in asphalt or in concrete. So those traffic loads definitely play a part. Now, within our pavement structure, we have a number of layers. We have the surface, in this case is asphalt. We will have some sort of a base material to support that. We might even have a subbase. And then below that, we have the subgrade. Now, every layer plays a part in spreading out the load that we're applying from the traffic. But what we see is just on the surface. So if we have some things going wrong underneath the surface, it's hard to tell that because you can't see it. It's covered up by that surface layer. But when we start to get cracks, those are openings in the pavement surface that are going to allow water to get into that entire structure. So the openings get a little bigger, so we see water infiltration into those layers, and it goes further and deeper into the structure. And then we start to see things like subgrade failures or base failures. Those are kind of what we don't want to see, because the problem goes all the way through the entire extent of that pavement section. It's not just the surface that needs to be fixed, but the part we see at the top is the easiest to get to, and that's kind of what we want to be able to fix. So the sooner we can get to that cracking and keep the water from getting down and destroying that subgrade, the better off we are. So those repeated bendings lead to cracking, and repeated deformation leads to rutting, and you can see how that will affect all of the layers of that pavement structure. So water's getting in and causing all kinds of problems. Now, in trying to identify what those problems are exactly, we need to look at some type of a pavement rating scale. So what is the condition of my pavement? How can I judge that condition? Well, there are lots of ways. Some of them are really simple. Some of them are really complicated. There is a PCI, or Pavement Condition Index, that is outlined in a specification ASTM D6433. And what this does is step you through the process of rating your pavement on a scale of 1 to 100. So 100 is good, just like grades in school, the higher the score, the better. And so we're hoping to have higher numbers. We don't want to see those lower ones. It's fairly objective, but the thing about this rating scale, it was originally designed for airfield pavements. If you think about that context, it's one isolated area for one particular purpose, and all of that pavement is probably very much the same. When we apply this same strategy to, say, a county road network or a city street network, we have lots of different structures within our streets. And so maybe it's not as consistent. And so within the spec, it recommends that you take a sampling, and it's pretty involved. It's pretty intensive on what you need to measure, what you need to do. But if you're only measuring a small sample of those pavement areas, that's not so bad. But when you have lots of different roadways, different traffic levels, different structures, a small sample is probably not the best thing to do. You need to get a more representative sample. Another way to do this is to perform a windshield survey. This is a very subjective way of looking at our pavements. It's just a visual categorizing of what pavements have issues, what pavements don't. So rating scales can look a lot different. If we get really particular, we can use that 1 to 100 type scale. We might use a 1 to 10 or a 1 to 5. The biggest things that we're looking for is to determine what the types of distresses are, the extent of those distresses, and then also the severity. Now, how do I get this data? We need to collect quite a bit of data, so I could go old-fashioned and get a clipboard and paper and pencil, take a tape measure out and start measuring some of this stuff, and that's a great way to do it. It's very valid. There are some methods that are much more intricate, use a lot of automated distress surveys. The picture on the top right part of the page is the automatic road analyzer, the ARAN. That's what RDOT uses. They collect a lot of information with lasers. They can drive basically at highway speeds and pick up as small as 2 to 3 millimeter width cracking. They can measure texture. It does all kind of stuff. It's really fancy. Gets a lot of great information. It's a little bit expensive. And so I would encourage you to think about what makes sense. The picture at the bottom is a vehicle that's mounted with cameras, and there are lots of kind of, no, maybe not lots, but there are some in-between types of surveys that can be used. And so you need something that works for you. But these cameras can pick up, it looks kind of like the Google car, but it picks up images and video footage of the actual roadway surface itself. So at any given point in time, you can identify the distresses on that roadway at a certain time, because we also need to monitor how these things are changing. So even if you do a survey and you went out with pencil and paper and did a really, really thorough type survey, you're going to have to do it again and again and again. So keep that in mind. It's not a one and done kind of thing, because the data does change and the pavement condition does. Now, pavement smoothness is one of the characteristics that has been pushed from the federal perspective, looking at smoothness and how that relates to pavement quality. You can get a lot of information this way, and generally if a roadway is cracked and rutted, it will have some bumpy texture which will be picked up. So it's a great way to find those things, but you don't really get enough data to know what type of cracking it is or what type of rutting it is. where some other systems you might be able to get a little more information. And we do need to know the types and what caused it to some extent, because we've got to figure out how to fix it. And if there are different causes, there are obviously going to be different solutions to help fix it. Now, again, we've got to figure out, what do we want to do? How do we want to collect our data and make sure that it makes sense? If you want a very high level of detail, that's great. For instance, a state network. If you're a large municipality, you have lots of high traffic volumes, it's, I would say, definitely worth it. It's more expensive. You get lots of data. There is some danger in having too much data. What do you do with it all? Who's going to manage it? Who's going to monitor that? Who knows what to do with it? So make sure that if you are paying the higher price for the more intensive details, that you have a plan to actually use that. Now, at a lower level of detail, maybe your local networks that have a lot of low and medium type traffic levels, you can save some money. It's much less expensive. You don't get as much data, but maybe it's enough for what you need. So just make sure you think through the process of what you plan to do with the data, who's going to manage it, are you going to test all of your roads? Do you think that it's reasonable to just get away with a sampling of those roadways and all those types of things? Because the most important thing is that if you're going to go to the effort to do all of this, because it's not easy, if you go to this effort, you want to make sure that it is fruitful and productive and helps you make good decisions on how to improve your roadways. Hey, at this time, let's stop and see if there are any questions.
Good afternoon, everybody. At this time, I don't see any questions that have came through. As Stacy was talking a little about earlier, if you do have questions, please feel free to post those in the questions pod, and you can post those now or at any time that we move along. And at the next stopping point, we'll get to those questions.
All right, let's move on and talk about asphalt cracking. All right, when we look at cracking, we're going to have to measure those cracks. Our first question is going to be, how severe is it? Which really means, how wide is it? A narrow crack is less severe. It lets less water into that space. A wider crack is going to let water, air, incompressibles, just, grit. Sometimes you see grass growing in a crack, other little rocks, pebbles, sand, all kinds of things there. And so that has the potential to do more damage. So it is considered to be more severe. We'll also be looking for whether or not there are adjacent cracks in that location, or if the crack edges themselves have deteriorated. Then we're also going to look at the density of those cracks. We may have a really severe crack, but there's not a whole lot of them. Okay, and that would be a better scenario than to have those large, severe cracks and have a lot of them. So we've got to look at both of those things. Now, low severity is considered to be less than 1/4 of an inch in width. Moderate severity is 1/4 to 3/4 of an inch. And then high severity is going to be anything over 3/4 of an inch wide. And you can imagine quite a bit of gunk and stuff can get down in there. Now, during the year, as the temperature changes, that crack width will also change. So that's something that you would also want to keep an eye on. Those cracks that tend to change quite a bit means that your pavement is a little more susceptible to temperature changes. So those close and open seasonally. So make sure that you're thinking about that based on the time of your survey. And when we're measuring cracks, the density is going to be sometimes a percentage. It might be based on linear footage. It might be the square foot of the type of cracking that you see. And then we can also just kind of put it into a relative measure. Maybe we feel like it's good enough for us to just call it high, medium, or low density, and that's okay too. Transverse cracking, those are cracks that are basically perpendicular to the center line. So they're going to run across the road side to side. But they're not going to be the ones that are caused by underlying concrete joints. That would be reflective cracking. We're going to rate the entire crack at the highest level present for 10% or more of the total crack length. So in the diagram, you can see there are a few cracks there. And so if we go along and measure those, on the left, we've got one that's a 1/4 inch. So that would be low severity. And then we've got one just kind of down to the right of that. Maybe you can see my cursor. That would be moderate severity. Also over here, we've got a segment that's 1/2 inch, and you see that the crack runs all the way across the road here. One measurement is 1/8 of an inch, another measurement is 1/2 inch. And as long as this is more than 10%, we're going to go ahead and rate this at the highest level, or the worst case scenario. And then over here on the right, we see another crack. This one's actually 7/8, 7-inch wide. So that is going to be high severity. And here are a few pictures of the types of cracking that we're talking about. We've got some transverse cracks that run across, and you notice that they're not real straight. If you have reflective cracking, sometimes we don't know what the underlying structure was, but reflective cracking would be a situation like if you had concrete pavements and that had joints, and then those joints reflect through as cracks after an asphalt overlay was done. You'll see those nice and straight, very clean across that pavement. And most of our transverse cracks that occur naturally are not that clean. So they'll kind of wander back and forth or have some wiggles and jiggles in them. The middle picture, you can see there are some random cracks that connect to other cracks. So it's a little bit more intensive. And then just another picture on the right, and you can see how it's not a straight line as it moves across the roadway. Now again, the severity is based on the crack width, but also the adjacent cracking. So the middle picture on that last slide did show some other cracking in that area. So low severity, again, the average crack width is going to be less than 1/4 of an inch. And it might be that it's a sealed crack and the sealant is still in good condition. Moderate severity, we're going to have an average crack width between 1/4 inch and 3/4 of an inch. Any crack adjacent to a low severity or random cracking. So now we're getting into some of those connected cracks. And then for our high severity, if we are a crack that is adjacent to a moderate or high severity random crack, then we're going to count it in that category as well. Okay, and again, average crack width is going to be those bigger ones, so more than 3/4 of an inch. And that's pretty significant. Those are definitely the ones that you can feel as you're driving down the roadway. All right, so how are we going to measure this and keep up with it? We're going to record the number and the length of transverse cracks. We're going to separate that by severity level, and we're going to rate the entire crack at the highest severity level present for at least the 10%. And the total crack length for a given crack is assigned to that severity level. So what we're going to end up with is a listing or a chart, however you want to do that, of coming up with how much we have of each severity level. Okay, we're going to record the lengths of the cracks with sealant in good condition. And just for context, generally, rule of thumb is that at least 90% of that sealant must still be in good shape. If the transverse cracking extends through an area of fatigue cracking, and sometimes you'll see that, a transverse crack across the road, but then there's a spot in there that's got that alligator cracking or fatigue cracking, then the length of the crack within that fatigued area is not counted, because we're going to count it with fatigue cracking, which is considered to be a worse type of cracking. And then anytime you see a crack that's less than a foot long, we're not going to worry about that. That one does not count. Okay, next we're going to look at longitudinal cracking, and these are cracks that are parallel to the center line, so they run long ways down the road. And the biggest thing that we need to consider here are whether those cracks are in the wheel path or not in the wheel path. If they are in the wheel path, they're more likely to be load related because that's where traffic sits, that's where the actual load is applied. And if they are not in the wheel path, then it's going to be more of a non-structural issue. Okay, so in this picture, you can see some longitudinal cracking. Those cracks are not in the wheel path. We've got them showing up at the longitudinal joint and then about halfway, like right in the middle of the lane. This one, on the other hand, is right where the traffic goes. So you can see, if you can see my cursor, right along here is the actual longitudinal joint. And then offset a little bit, we've got this longitudinal crack. This one's actually really nice and straight, but it is in the wheel path, which is going to indicate a load-related failure. Now for longitudinal cracking, we've got kind of the same scenario here. Low severity is less than 1/4 of an inch. Same deal with the crack sealant being in good condition. And then our moderate and high severity will be 1/4 inch to 3/4. High severity is more than 3/4 of an inch wide. And then we have some considerations of that crack being adjacent to some random cracking as well. All right, now, when we're looking at longitudinal cracking, we're going to look at those that are in the wheel path and record the length of those cracks. And we're going to separate that by severity level. So any longitudinal cracks that is associated with random cracking, that means we've got cracks running in different directions. That's going to be more like alligator cracking, and so we're actually going to rate that as fatigue cracking. So we'll separate that out from the longitudinal portion. If it is a longitudinal crack that meanders quite a bit and has a quantifiable area, we're also going to rate that as fatigue cracking. If it's outside the wheel path, we're going to record that separately. And again, we're going to record the lengths and separate by severity level. Now we're going to get into fatigue cracking, and this is the kind of cracking that we see that's really based on the repeated loads caused by heavy traffic. In the picture, you can see some definite deterioration. You can see trucks in the picture, so we know there's a lot of heavy traffic. And then those distresses, you can see exactly the pathway falls right in the wheel paths. And so that's usually where this type of cracking will start. So low severity fatigue cracking has few or maybe no connected cracks. The cracks are not spalled. They've not yet been sealed. There's no pumping evident. We're just starting to see those beginning signs of deterioration in the wheel path. So something like what you see in that diagram. And then for moderate severity fatigue cracking, we're starting to see some of those interconnecting cracks forming a pattern. So the cracks may be slightly spalled, and spalled means that the edges of those cracks have broken, so it looks deteriorated. It's not a clean break, it's kind of mottled. Those cracks may be sealed, but again, we're still not really seeing any pumping. And then for our more severe level fatigue cracking, we've got interconnecting cracks that are forming a pattern. It's very obvious. It starts to look like an alligator, so that's why a lot of folks do call it alligator cracking. These cracks may be moderately or even severely spalled, may or may not be sealed, and at this point, there's a higher likelihood that we are seeing some pumping. Now, if you're wondering what pumping is, it's just like what you see here. Some of the underlying material, such as the subgrade, has actually been pumped up through the surface. And so we see that happen a lot during a rain event. That soil material comes through the cracks from the bottom up. And then after the water dries, we see it just looks dirty. And that's the residue from that subgrade material that's left over. So it looks like it got dirty on the surface, but it actually came from underneath. There we go. Here's another example. This is some pretty defined alligator cracking, so severe level fatigue cracking. And again, we do see the evidence of that subgrade material being pumped through to the surface. And after that pavement dries, we're left with that residue, so it has a dirty look to it. And then here's one where we do not actually see pumping, but that is some extreme fatigue cracking over in that lane. So lots of interconnected cracks. Now, in terms of measurements and how we record this, we're going to report it in either square feet or square yards. And we're going to separate that by each severity level. So if you're doing that and you really can't figure out which one is which, or maybe part of it looks medium, part of it looks severe, go ahead and rate it kind of worst case. So the highest severity level that you see in a particular section, go ahead and assign that. Now, fatigue cracking is interconnected cracking, but it's very much related to a load-based problem. Block cracking is kind of like that in that those cracks are interconnected, but it's not really, it's not necessarily load related. In fact, it does not start out that way at all, but it's more of a block shape. So you'll see some squares, and it's not going to be super straight lines, but you will notice that there's a pattern of similar size, either squares or rectangular pieces that are kind of separated out. And those blocks can be anywhere from 1 square foot up to a 10 by 10, 100 square foot. So it just depends on the pavement. In the diagram on the left side, you see the smaller blocks, and on the right side, you see like one big block. This can be in combination with fatigue cracking. And the part about this that's a little bit tricky is that block cracking by itself is a non-structural type of cracking. But after you have, even if it's non-structural, that's a good thing. But if you don't treat that and you don't fix it, then putting traffic on top of a pavement that does have a crack, letting water infiltrate and all those other things that go along with cracking, it will slowly turn into fatigue cracking. So sometimes we see that intermediate phase where it's kind of turning from block cracking to fatigue. So it can be in combination. So some early stages of block cracking, we start to see a little bit of that non-structural longitudinal cracking. We see transverse cracking, and then we start to see a more regular pattern develop, but it's not isolated within those wheel paths. And again, it's important to watch this throughout a period of time and kind of keep up with it, not just to check it once and you're done, but to get an idea of how it's changing and how it's modifying. Okay, and then another one you can see, I think the probably most typical size blocks are going to be 2, 3, 4 foot by that same size. So kind of in between those extremes that I showed you on the diagram in the previous slide. Now for block cracking, our severity level is going to be based on the crack width and the adjacent cracks again, so much like what we've seen before. Average crack width for low severity, less than 1/4 inch. These may be sealed, which means you can't really see it to figure out what the width is, but that sealant being in good condition is a good thing. Moderate and high severity, again, like what we've seen before, it's going to be based on the width of the crack as well as that adjacent random cracking. Now, how do we measure block cracking? Well, we're going to record the square feet or the square yards at each severity level, but one of the caveats here is that to consider it block cracking, the length of the affected area should be at least 45 feet long. So if you have just a very small spot, maybe 10, 20 feet long, where it looks like block cracking, that's actually not going to count as block cracking unless it is consistent over at least 45, 50 feet. If you have fatigue cracking that is also in that area, then you're going to reduce the block cracking area by the area that's fatigue. So you're going to have to separate out which part am I going to call block, which part am I going to call fatigue. Right now, reflective cracking. We've already mentioned this one. This is where you might have an asphalt pavement on top of an older concrete pavement that was jointed, and then those cracks from the joints reflect through. So we need to know how can you tell the difference in transverse and reflective? And sometimes it's really easy, sometimes it's not so easy to tell the difference. So if you have some information on the construction history and you know that it used to be a concrete pavement, great. That is wonderful information to have. You don't always have that. But when an asphalt surface is placed on top of that concrete, whatever gap is underneath it, that's a break in the support. And so we have that weak point, and that's why it's always going to reflect through. And usually there's no magic that will fix that. You will always have that. There are some treatments that can slow that down, but there's nothing that's a magic. This will always fix it kind of a thing. But you'll notice things like it's very uniform in spacing. You might notice the transverse as well as the longitudinal blocks, depending on the width of that pavement. But a very even spacing is typical. And really that historical knowledge is going to help you more than anything. But in the diagram, you can see there's a transverse crack that's not really straight across the road. They would have never cut a joint in concrete like that. So that's going to be classified as a transverse crack, where these ones that are really straight across. And then also don't forget, we have these longitudinal ones that can be a reflection crack. That gets a little tricky because we can have cracks at the longitudinal joint for the asphalt, but also if those lanes were paved separately with concrete, we're going to see that reflect through as well. So that's typically a pretty weak spot regardless. All right, reflective cracking severity. I'm going to kind of skip over this because it looks just like what we've seen before, but we're going to be at less than a quarter, more than a quarter, and more than 3/4. And here's an example of some reflective cracking. You can see exactly where those slabs were in that underlying concrete pavement. And then we might also see thermal cracking. And this is cracking that occurs due to temperature changes and really just the shrink and swell of that ribbon of asphalt as it moves through that area. A lot of our designs over, I would say, the last 20, 25 years, once we started using SuperPave and paying more attention to the temperature ranges for the binder, we're seeing less of the really true thermal cracking issues. We might also see edge cracking. This is something that is going to apply to the pavements with unpaved shoulders. And usually it's going to show up as kind of a crescent or a little bit of a curved breaking off section right at the edge of that pavement, because when we don't have a paved shoulder, we don't have that lateral confinement or lateral support. So it's easy for that edge to kind of crack and break off. But we're going to classify those for anything that is located within 2 feet of the edge of the pavement. and this will include longitudinal cracks that are outside of the wheel path. All right, low severity for edge cracking is going to include cracks that don't have any breaking. There's no loss of material yet. We're just seeing that the crack is there. But then moderate severity will be where the cracks are starting to break up a little bit, up to maybe 10% of that affected length might have lost some of the material. And then when we're losing more than about 10% of the edges, we're seeing chunks break off of that edge, we're seeing a lot of breaking up, that is going to be considered high severity. So you can see kind of what that looks at. We do have a little bit of breakup there. We're going to record edge cracking in terms of the length of the affected pavement edge. So how long of a span is that problem happening? We're going to have that separated by severity level. Okay, and here's one that has quite a bit of breakup at the edge. And none of that is so far that it's over into the wheel path. So it is all considered edge cracking. Okay, another thing that we might need to document on the edge of the pavement is that lane to shoulder drop off. When we don't have paved shoulders, we have the potential for a vertical differential there where that gravel or crushed material that's pulled up to the edge, that will tend to wear away, especially if we have traffic that's getting over on the edge and wearing it down. So when that difference in elevation is more than about 2 inches, there's a definite safety issue at hand. So what we want to do is record that elevation difference so that we know what that is. So if you're seeing any significant drop-offs, make sure and record that. Slippage cracks are another type of cracking, and this is really where the asphalt is not bonded well enough to what's underneath it, or it's been flexible enough that it pushes so much that it finally breaks and pulls apart. So you see this on steep downhill slopes. You can see that since it is a crack, the picture on the left looks damp. Water is infiltrating that area. The picture on the right, this is pretty common as you pull up to a stop sign or an intersection or something where the vehicle is changing momentum. And you can see a couple of places where it's literally just pulled the asphalt apart as the trucks pull up to the stop sign, and that braking action is putting lateral forces and just pulling it apart. This is a little more extreme case. We've got some tearing of the asphalt and then a massive crack in the picture on the right, and you can see how that's holding water. So water is the enemy. This is definitely what we don't want to see on our pavement. All right, any questions?
All right, looking through, it looks like at this time we do not have any additional questions.
Good deal. We will keep moving. All right, so I have a question for you. I'm going to have you name that distress. If you'll just use the questions pod to type in what type of distress you would call this. And then if you want to put in also what severity level, we're not going to know the density because you can't see enough of that roadway, but just a guesstimate of what severity level and what type of distress. I'll give you a minute to type those in. All right, very good. This is transverse cracking. It runs across the roadway. We can't actually measure it, but it does look like it's a little more than 1/4 of an inch, probably not 3/4 of an inch. So I would call that moderate severity. Also, you can see a little bit of deterioration and random cracking along the edges. So right here, we see that a piece is kind of broken off. So that would also indicate moderate severity. Good job. All right, now let's talk about asphalt rutting. Rutting is pretty self-explanatory. We know what that is, but it will have some longitudinal depressions in the wheel paths of that lane. So you can see here some evident um, differentiation. It's not a smooth cross section of that roadway. This is a more severe case of that. We've got some definite issues here. You can tell where the loads are being placed, and it's really just pushing that mix around and moving it. So we have some low points in the wheel paths. Now, the two ways that rutting can happen, the first is in the subgrade or the base layer. And so really what happens is that the deformation happens well below the surface. So the subgrade might be weak, it might become soggy and saturated, and a little squishy, and then we put that traffic load on it. And so we see that subgrade deforms, or it could be in the base layer where it deforms, but typically it's going to be in the subgrade. We specifically designed the types of materials that we're going to use for the base and for the surface, but we tend to use whatever's there in terms of subgrade because it already exists. So unless we do some type of a modification or improvement to that subgrade, we're really just using that natural resource. And a lot of times that will be susceptible to some deformation when it gets wet, especially if it has much clay in it. Now, the other option would be that the subgrade's fine, the base is fine, but that asphalt mix is just a little bit too weak for the type of traffic that we're going to put on it, and it moves around. So in the case where we had, let me actually go back. In this, if you look at that original cross section with the straight line, everything that moved down to make the ruts went downward. Nothing went up. On the other hand, if the mix is the problem, then whatever moves down here, it's going to hit something solid. It can't continue to go down, so it's going to move the mix side to side. So we have these extra heaps of asphalt that have moved to the outer edge of the wheel path. We've got a lump here in the middle of the wheel paths, and then another hump over here. So there are some mix below and some that has moved above that original profile level. That's going to indicate that it is actually rutting because of the asphalt layer itself. And that's what you would like to see. That's best case scenario because that's all you have to fix. It's just the top layer. Now, in terms of measurements for rutting, what we really want to know is how deep is that rut? Again, it is a longitudinal depression in the wheel path. Officially, severity levels are really not assigned because a rut has safety issues associated with it. So if there is a rut, water can sit in those areas of the pavement and cause hydroplaning. It could freeze. Lots of things that deal more with safety. So officially, there are no severity levels. However, just as a rule of thumb, something less than 1/4 of an inch is going to be considered not so bad. Moderate would be quarter it to 1/2 of an inch, and you've got some serious considerations if it's more than 1/2 of an inch of rutting. So this is something you would measure with a rut bar. So a straight edge that you can lay across the width of the pavement and then measure from that bar down to the bottom of the rut at its steepest point. So something like this. And when you zoom in on that, you can see, hopefully no more than 1/2 of an inch, really hopefully no more than 1/4 of an inch, hopefully none at all. All right, so in this case, we've got a picture of a roadway where we've had some rutting. You can see that there are some changes. It's not nice and smooth across the width of the lane. And this one is actually a little bit of both subgrade and mixture rutting, but you can definitely see that there's a hump right here. So in between the wheel paths, we've had some mix move upward. The other indication of mixture rutting is that the stripe moves a bit. It's not super straight. So right through here, it looks straight, and then it's pushed out a little bit. That is also an indication that we've got some mixture rutting. That surface has moved. They didn't paint the stripe crooked, hopefully, but that tells us that that mix is moving a little bit. Now, based on core samples, we also found that there was some subgrade issue, and we had to deal with that as well. So this is really a combination problem, but those are a couple of the things that you can see right off the bat in the picture that would identify mixture rutting, because it's all easy to tell you, you know, with that line, here was the original profile, but when you walk out onto the pavement, that line is not there. You have to just be able to look at it and tell where was it originally, and that's not always the simplest thing to do. A related distress that's kind of like rutting is shoving. And this is displacement of an area of the pavement surface. And that's usually when you have heavy traffic putting on the brakes or maybe accelerating, but they're doing something that's changing the forces on those pavement sections as compared to where there's just normal driving. So this is really common to see on hills. You might see it laterally on curves and coming to an intersection. So as that truck comes down, it puts on the brakes and it's actually shoving the asphalt forward based on that friction. In terms of measuring, we're just going to record the number of times that it happens and how many square feet it affects, because this is usually going to be an isolated area in a curve near an intersection or something like that. It's not going to be spread out throughout the entire traveled way. Here's another example of shoving. You can see how the surface of the asphalt looks kind of lumpy. That is just the effect of traffic coming to an intersection. So you've got both the braking action and then also the acceleration. At this particular location, it's uphill as they're accelerating to take off from that stop sign, and at an angle that's pushing the asphalt around. And then another example here where we're going downhill in these lanes that are more on the left side of the picture. You can see some more extreme. It feels like washboarding, but it's just some shoving as you come down the hill, approaching a stoplight, and it always seems to be red right there. So everyone has to put their brakes on. They push the material forward, and then it just makes it lumpy, makes it rough. And then the rougher it gets, the more of an effect it has for the next bit of traffic that comes along. So it continues to get worse. And then here's an example of lateral shoving in a curve section. The best way to identify this, again, is to look at the stripe. The stripe was not painted in a wavy format, but it looks that way now. And so what's happened is traffic is actually pushing that mix around. It's not super stable. So for that, we're going to look at the square footage, figure out how much of that pavement is affected, and record it. Now there are a few other asphalt distresses to look at. Bleeding and flushing. This is really just excess oil or binder. If your mix was too rich, compacted too tight, and that bled to the top, this can create a loss of surface texture. This is a safety issue again, so we're really not concerned with severity levels. You can probably look at it and tell some are worse than others. The one in this picture is pretty extreme. But officially there are no levels. So it's a problem that does need to be addressed. This is a more mild case. Again, no severity levels, but you can tell this is not going to cause the same level of skid resistance issue that the previous picture would. But we can see that this is happening because there are darker sections within the pavement. That's an indication that the binder is sort of flushing or bleeding toward the surface. A brand new pavement, you won't really see that so much because it all looks black. It's fresh, looks good. But over time, those binder films at the surface do wear away. So when you start to see the darker color reappear, that means the binder is coming from somewhere down within the mix. So it's moving toward the surface. In terms of measurement, we're going to record the square footage of the affected surface area. Now, the biggest issue with the bleeding and the flushing is skid resistance. So rather than looking at something like a severity level based on a measurement of what it looks like, we can actually measure the skid resistance itself. So there are a couple of things at play when we talk about skid resistance. One is microtexture, one is macrotexture. There is a British pendulum device that you can use. A lot of folks have it, but what it does is uses a rubber foot on this pendulum. Right now it's in the locked position, and then you place that on the pavement and then push the button, it drops this foot and it swings. As it swings, that rubber foot will graze across the pavement and generate a level of skid resistance that is indicated on the scale over here on the left side. So it's a relative measure that will tell you which pavements have more or less skid resistance. So that really deals with the microtexture, which is kind of the grit and the grip of the aggregate particles themselves. Now the mix will have a macro texture. There will be some little spaces and that kind of that bigger texture, which is why it's called macro texture. But those are the spaces within the surface of that mix where water might be able to sit temporarily during a rainstorm to keep it from being right on the surface. If everything is super, super smooth, there's no resonance area for that water, and so it's just going to come in contact with the tires. But if we do have a good amount of microtexture, that water can live somewhere until it can run off and keep it from breaking the bond between the vehicle tire and the pavement surface. And one of the tests for this is a sand patch test. You take a very specifically graded sand, specific amount of that, and you put it on the surface and then spread it out and see how much surface area it takes to contain that particular amount of sand. And the larger the circle is, the less macrotexture you have. So if there's a lot of texture, it can hold that sand in a smaller area. Then you measure the circle. If there's a low amount of texture, then that's going to spread out a lot further. So that also gives you a relative comparison of the amount of texture. There are some fancier ways to measure skid resistance. RDOT has a skid trailer. They spray water and then they'll lock up the brakes at a certain speed and see how much they skid, and that provides a skid number. And I believe typically the minimum skid number that's allowed is 30. Anything above that is good. In addition to that, that automatic road analyzer, that van, again, very expensive, but this is one of the measures that it can provide while it's doing its run, in addition to the cracks and the rut measurements and so on. The picture in the bottom middle is the circular track meter. This is more of a laser texture meter. So that sand patch test that I showed you, this is a fancier way to do that. So it uses a laser that moves around in a circle underneath that silver box, and it actually measures the amount of texture for that track or for that circular area. And then at the top right is a dynamic friction tester, and this is one that it's got a motor, so it basically spins that rubber foot. This would be the comparison to that British pendulum that I showed you a couple of slides ago, but it gets the speed up to 80 kilometers per hour in a little circle under there. So the motor gets it going. There's a hose to spray some water on the pavement, so it's like a wet skid test, and then it drops that fixture, and the rubber skids, they actually screech, so it will scare people out in the field when you're running this. But it will run, it will drop, and it will give you a skid number based on that wet test. But it's a portable type of test. It's kind of cool. Gives you a good relative measure as well. Okay, another place where we might need to do some friction testing is when you see polished aggregate. This is where the surface binder has worn away, the aggregates are exposed, and we would like to think that our aggregates still have a lot of texture, both micro and macro texture, to provide that skid resistance. But some aggregates kind of get smoothed off or polished by the action of traffic. So then we lose that friction. And again, we're not really going to look at severity levels here. We could do some skid testing and determine whether it's good or not good, but it's a safety issue. So we're not going to have a low, moderate, or severe. When we have polished aggregate, we're going to look at the square footage of the affected surface area, and we're not going to count any sections. Sometimes we'll have something that's got preventive maintenance applied, or maybe we've got a crosswalk with some different texture. That part is not going to count. We might have some pavement sections that exhibit raveling or weathering. This is where we have a loss of surface aggregate as well as binder. Sometimes we lose the fine aggregate. Sometimes we lose fine and some coarse aggregate. And sometimes we lose coarse aggregate too. So it could be all of those things. But if you look at this picture, you can tell it didn't start out with that type of texture. We've lost some parts of that mix. So typically we'll see this in older pavements. Weathering just happens. It's out there for lots of years. It's in the weather, and then it does start to ravel and lose some of those particles. When we're measuring this, we're going to look at the square footage of the affected surface area. We're going to make a note of the type of aggregate that appears to have been lost. But this is not something that we're going to rate on chip seals. Now, we do have raveling on chip seals, but when we're doing our pavement surveys, we're not going to worry too much about those details on that type of road. But you can see there are two different examples here in the pictures that have very different textures. And so that gives you an indication of what types of aggregates are coming out of that surface. And then you might see something that's very closely related. These are pop-outs, and this is where you're just losing those larger coarse particles. If that's happened over an entire area, it's going to have a really rough-looking texture. But just as a close-up here to see what that looks like, it looks like one big rock just sort of got plucked out of there, and that is exactly a pop-out. Okay, we're going to need to note things like water bleeding and pumping. So if we see water seeping from underneath the pavement and it's coming up through those cracks, that's definitely something we want to notice. At that point, we've already talked about how some of those fines may come up through those cracks and be left on the surface, just kind of looks dirty. So we're going to measure the number of occurrences and how much length of the pavement is affected. And we're only going to count it if it's 3 feet or more. If it's just a small spot, we're going to ignore that. Okay, so we might see that it's just water that's coming through, and we have to kind of pay attention and know what kind of weather has been happening. If we see something like this, you need to know, did it just rain and everything else has dried, but there's more water near those cracks, which is what helps them show up. But if it's just that it rained and this has not dried yet, that's different from it hasn't rained in 3 days and this is still wet. That's an indication that water is pumping back up through from the bottom side. So it's a different action. Okay, then we're going to also measure potholes. This is kind of a bowl-shaped hole. Y'all know what a pothole is, but different sizes, different depths. Anything less than about a 6-inch diameter is not going to be considered, but we need to know the depth. That's going to determine our severity. So low severity is something less than 1 inch. Moderate severity is 1 to 2 inches, and high severity is going to be anything more than 2 inches. Now, a lot of times our potholes are dependent on the layer of that pavement that failed. So if it is, say we had some fatigue cracking on a pavement that was a 2-inch overlay, 1.5 to 2 inches is a typical overlay depth. And then it's just that portion that has broken apart and popped out of there that leaves a pothole. So that kind of a lot of times will indicate the severity, because if it's just that layer, it's probably going to be a moderate severity pothole. But if there's been more deterioration and it's deeper than that, maybe the underlying layers have also come out, and then we're going to be in more of a high severity. Right, and then there will be places that were potholes or different deteriorated portions that we patched previously, and we need to look at the condition of those patches. That also affects the overall quality of that pavement. So a patch is a portion of pavement that's been removed and replaced or additional material applied after original construction. So we want to look at those, and we're really just going to look at these and see what distresses they have, just like we would look at any other pavement, but we're going to categorize these in a separate section. So low severity has any low severity distress of whatever type. Moderate severity, whatever that distress is, we're going to use the criteria for that particular distress, as we call it, low, moderate, and high severity. In terms of measurements, we're going to record the number of patches, and then we're going to also look at the number of square feet of the affected area for each severity level, and any distress in the boundary of that patch is going to be included. Okay, and then a distress that's usually pretty hard to see or truly identify without coring the pavement is called stripping. And this a lot of times will show up from the surface and look kind of like rutting, but it's where the binder films within the mix are separating from the aggregate. You know, asphalt is rocks and the oil coats the rocks and sticks them together. But when the oil comes loose from the rock, then we're going to see some, the lighter color is really just broken rock, but you can see a lot of places where it's brown. That is where the binder films have actually separated from the aggregate surfaces. And so what that means is we don't have that adhesion. We don't have it all locking up. And so it gets a little extra mushy, and that's where we see rutting at the surface. But it's not our traditional type of rutting. It's specifically because we've lost that adhesion between the materials. All right, that's all on asphalt distresses. Are there any questions?
Yeah, it looks like a pretty quiet bunch today. No new additional questions.
All right, well, we will keep moving. And y'all can probably tell I'm a little bit under the weather, so I apologize for the sound quality of my voice, but we'll do the best we can and keep moving. So at this time, I've got some questions for you. If you would use the questions pod to type in your answers, can you name that distress? And I'll give you a minute to look at this one and see what you think caused this actual distress. All right, good answers coming in. Looks like we've got a subgrade failure, and that is most often due to water. So it's a low spot. We would possibly put this in the category of rutting because we do have a depression here. We also have the appearance of some fairly high severity cracking, looks like fatigue cracking because those cracks are interconnected, but it is in an isolated area. And then over next to the curb, you can see that loose aggregate coming through. So that could be a sign of base material coming back up. It could also be possibly stripping. We would have to core that to figure that out. But in reality, what's happening right here is if you look across the sidewalk, you'll see that there's a fire hydrant. And this is it's zoomed in, you can't see the overall area of pavement. But when you have this very small, isolated failure, everything else on the street looks very good, it's in good shape. Look around, because our number one problem is always water. So drainage, drainage, and drainage comes back to us again. And in this particular location, there's a fire hydrant. So best guess is that there's a small water leak within the piping under that hydrant that is affecting this exact section. So that is something to look at. Sometimes you can help out your water department and find the leaks for them based on some of the distresses we see in the pavements. All right, so now looking at structural versus non-structural, we hope to see non-structural issues because we have a chance to fix those before they become structural problems. Structural problems are deep problems. They require a deep solution. So we're going throughout the extent of that entire pavement structure to truly provide a substantial fix. So the kinds of things that are going to be a little more user-friendly will be transverse cracking, longitudinal cracking that's not in the wheel path, block cracking, raveling and weathering, bleeding and flushing. Mixture rutting is also one that really is limited to that top layer. So that's something, these are all things that we can fix from the top side. So when you're looking at some of your treatment options that are more surface related and less of the rehabilitation, reconstruction kind of things, this is where you can catch it early and you can get some things done for a much lower cost. If you wait longer, or if those distresses are already structural, you're going to see things like longitudinal cracking in the wheel path, alligator cracking or severe fatigue cracking, your base failures, pumping. That's an indication that things are not all well with the pavement structure because we're losing part of the subgrade and it's coming to the surface. And then also subgrade rutting. So again, these are things that we can put overlays, we can do some things to patch it, repair it, that will buy us some time, but it's not truly going to bring us back to a condition that we can expect significant longevity for the life of that pavement. All right, now we're going to switch gears a little bit. We're going to talk about some concrete distresses, and really concrete just breaks. It cracks. Concrete is a rigid pavement. It contains water, cement, sand, and rock, maybe some admixtures. But the water and the cement really do the work. So the cement is the magic. It reacts with the water. There's a hydration process that creates that paste that hardens around the aggregate. So the aggregate's really the filler, and the concrete gives it all of its fanciness, all of its strength. So when we have deteriorations, that rigid pavement doesn't bend, it doesn't flex, it doesn't rut, doesn't do any of that, it just breaks. So we see a lot of different types of cracking. So for concrete distresses, we're going to look for corner breaks. We might look for joint seal damages, joint spalling, faulting, map cracking, scaling, polished aggregates, pop-ups, pop-outs, blow-ups, and another one we might see is alkali silica reaction. Now, corner breaks are kind of common, I guess, because typically when we have concrete pavements, we're going to put joints in that. Concrete cracks, and concrete's going to crack no matter what we do. So the way that we attack this is to say, hey, we know it's going to crack, let's go ahead and put in our joints. So we'll saw cut that during the construction process to control where those cracks go. If we can make them nice and straight, we're going to preserve the functionality of that pavement for a longer time. So we put in those joints and then we're forcing the crack to happen at that location. So we kind of have these individual slabs that don't totally function independently, but a lot of times the distresses are isolated within a certain slab. Now, a corner break means that the corner breaks off of that slab, and it will be somewhere close to a 45-degree angle. And the length can be anywhere from 1 foot to like half of the slab width. Slab width is typically lane width, or maybe lane plus a little bit of a shoulder. All right. Now, if we look at severity levels, low severity is where less than 10% of the length of the spalled area, or less than 10% of the length of the crack has spalled. No measurable faulting. The corner piece is not broken within itself. No material loss, no patch, all that kind of stuff. Moderate severity will have more than 10% of that length spalled. And again, spalling is where the edge of the crack itself has deteriorated. So let me actually go back one slide and show you in this picture. You notice how further up here, this is where that saw cut was made. And then we've got some areas that got a little icky. So the edges broke off, and you can see those broken sections. That is spalling. And then high severity, we've got more than 10% of the length spalled, and then faulting of more than a half of an inch. The corner piece may be broken, which means there'll be another crack within that triangle. And there might even be some patch material in there where there's been previous attempts to fix that. So here's an example of a corner break. You can see how the slab goes, and then we've got basically a triangle formed where the corner has broken. So that's exactly what it says. Now in this case, we've got another one. You can see a pretty good break there, and then also some spalling, some deterioration, and loose material within that broken spot. A little bit of patch material was attempted there, and you can see the remnants of that as well. Now, durability cracking, also referred to as decracking, is where we have some closely spaced crescent-shaped kind of hairline-looking cracks that run around the edges of those individual slabs. So at the corners, we might have some of those really thinner-looking cracks. So low severity, really no missing material. It's kind of a tight pattern. But then when we start to see more of a well-defined pattern and maybe a little bit of missing material, that puts us in the moderate category. And then if we have really developed cracking, missing material, that's going to be considered severe. This is an example of the kind of thing. It's a very definite pattern. You can tell those crescent shapes that run right around the corners. It's in the areas that would have corner breaks, so you typically either see corner breaks or you'll see the durability cracking. Okay, spalling, again, we talked about this. This is where the crack or the joint itself has some deterioration in different sections. The picture on the right has a little bit more extensive deterioration that we can see. And then faulting. And faulting is also related to pumping. What you see here is that those slabs, if they don't have dowel bars or some kind of a load transfer device built in, then we're going to see that that slab is completely independent of the one that comes next as traffic moves across. So when that wheel load moves forward, it's going to push down and apply that load. And at the edge of the slab, we have the least amount of support sometimes. And so then as the wheel moves across, the first slab will pop back up. The second slab gets pushed down. So if we go kind of back and forth and look at that action, that will tend to pump material from underneath the slab up to the surface. So we saw pumping with asphalt pavements. The same thing happens here. So a lot of times when you're, say, going down the interstate and you see you're behind a big truck and they go across a wet spot and a lot of dirty water kind of shoots up out of that crack behind them. That's what's happening. They've hit that first slab, pressed it down, and then they've moved across the joint to the next slab, which has sucked some of that dirty material, some of that base material and subgrade, and then it just squirts right up behind them. So you can see that happening. That is a loss of material under the corners of those slabs. So when that happens, we know that we don't have the same amount of support at the joint that we have during the mid part of the slab. So that's going to make the road quite a bit rougher at a quicker pace. So faulting and pumping is definitely something to look at. Scaling is another thing that we have issues with. I will say that you don't see this as much on roadways, but you see it a whole lot on driveways, sidewalks, that type of thing. And typically what's happening here is there's just too much water that got added. Adding water to concrete makes it easy to smooth out, makes it a little more liquidy, easier to work with, but it does not help the longevity. So what happens then is that water, the water cement ratio is not quite right for what ends up at the surface. So as it's finished off, we've got kind of that thin, watery, pasty layer at the top. And over time, that will just break off. So it's a thin film that wears away, breaks off. Another distress is blow-ups. And this is where we have a lot of thermal dimensional change. So in this case, the concrete was placed. This is a sidewalk. I've actually seen this happen on an interstate, and it will launch cars into the air. It's a very abrupt, it blows up. It's almost like a bomb went off. But the concrete has so much pressure built up within it because it's expanding, and there's nowhere for it to go, so it has to go up. So then when it breaks, it's very sudden, breaks, and it just has nowhere else to go, so it moves up. It does break the slab, and it's a pretty catastrophic event. Now for concrete repairs, there are a lot of different ways we can fix things. We can do a partial or full depth slab repair. We can rubbleize it, which means totally break it down and basically treat the concrete that's broken up like an aggregate or base. We can break and seat, which means when the material underneath the concrete has worn away, we've had a lot of pumping, sometimes we're better off just to break it into smaller sections and let it seat more completely over that base material. There are some thin and ultra thin white topping options. Typically, we don't see a lot of concrete placed in thin layers because it doesn't tend to last as well, but there are some technologies now with some thinner options. Hydro demolition and latex modified concrete's used a lot of times for replacing bridge decks. There's some ultra high performance concrete, because one of the things with concrete that's so difficult is that we've got to maintain traffic. And when we go in and do any major maintenance on concrete, we are shutting down the lane for a significant period of time. And that's difficult when you have a lot of traffic. So remove and replace diamond grinding, slab jacking, dowel bar retrofits, cross stitching, joint seals. We can even overlay it with asphalt. Lots of things that we can do, but again, a lot of these techniques are going to require that the road, or at least that lane, is shut down for an extended period. And the ultra high performance concrete is going to let us get something that's got high strength, high early strength, so that we can get traffic on it a little more quickly. All right, any questions on the concrete section?
Okay, no additional questions at this time.
Good deal. All right, at this time, I'll let you tell me a little bit in the questions pod about the distress type, what you think about the severity, the extent or density, and also is it structural or non-structural? So in this picture, we see a crack. So tell me what type of crack that is and how severe you think it might be. And then you can put some other information in there too. All right, very good. I see some answers coming in. We've got a longitudinal crack that runs long ways down the road. So it's parallel to traffic, parallel to the center line. And the location is what's important for a longitudinal crack. So this one is right in the middle of the lane, which means it is not in the wheel path. So that's important to us because that tells us that it is not a structural type of crack. Okay. In terms of the extent or the density, it goes as far as we can see through down the road in this picture. So we would need to measure the length of the pavement that's affected by that. Severity-wise, we don't have an actual measurement. We do see a little bit of vegetation starting to grow in that crack. So that is probably getting close to the 3/4. I would say it's 1/2 to 3/4 of an inch. There may be some sections that are high severity, but remember the breaking point is the 3/4 of an inch. Oh, good job. All right, how about this one? Let's do the same thing for this one. All right, very good. Looks like everyone has correctly identified this one as fatigue cracking or alligator cracking. Severity level would be high severity. It's very well developed in the wheel path, so that's how we know it is structural. This is in the wheel path, so it's load related, and to fix this, we would have to do something pretty deep within the structure to truly fix it. All right, very good. Let's see about this next one. If you were performing a pavement survey, how would you rate this section of pavement? All right, good job. And this one, we really have a pavement that's in decent condition, but we've got a few small cracks, and this is highlighted by the dampness around those. So this one just screams drainage, drainage, drainage. So part of the questioning here then is to decide, is the water coming from the top or is the water coming from the bottom? And I think we've got a little of both. You can see that this section is super elevated. So we got a higher elevation on the right side of the picture than we do on the lower side. And we've got more extensive cracking right over here in the lane on the left side. So it'd be oncoming traffic. Possibly a small section of some alligator cracking with pumping, but we're seeing water that comes through, and there's a high likelihood that this is between the asphalt layers and moving across. Water's going to flow downhill, so it's going to find the lowest point and it's going to come out wherever it can get there. So having that moisture underneath this pavement layer has allowed this deterioration to go a little bit quicker. So it's not terrible. It's not high severity or anything. It does look like it's probably rained recently. So this is something that's not a huge deal that on some days we might say, not a big deal, not going to worry about that. However, remember that this is the entrance for water and everything else to move through your pavement, which we don't want. When that starts to happen, we're separating portions of pavement, losing that support and that interlocking feature that helps the pavement stay intact. So the sooner we address these kinds of things, the more we can prolong the life of the pavement. Now, this wetter spot over here on the left, I would say we need to look, where's the water coming from? Maybe over here in this ditch on the other side. And is there anything that we can do to prevent that water from getting in between those layers? All right, and here is another one. Let me know what you think about this one. What distress is it? What severity level? And what density level for what you can see in the picture? All right, and these two pictures are actually separate pictures in the same general vicinity on the same roadway. So we've got a variety of distress levels, but the distress type is going to be fatigue cracking or alligator cracking. And in the portion on the left, I would still rate that as severe. We've got a lot of interconnected cracks, definitely in the wheel path, but it's very well developed. So that's going to put us into the severe category. The picture on the right is exceptionally well developed, but also shows a lot of pumping. So we've got a lot of debris, subgrade material that's moved through. We've got one little pothole that's developed at the top of the picture. So this is even more severe, but all of it, in my opinion, would fall into that severe category. So it's definitely a structural issue. The density, you can only see what you see in the picture, of course, but this does go down a pretty significant portion of this roadway. And this is actually a bus route leading to a school. So there's some, very routine, heavier traffic. So something that's definitely in need of repair, and it is a structural issue, which means it requires a pretty significant full depth type of repair to really make that repair last long term. All right, and here's one. Tell me what you think about this one. Type of distress, severity, density, structural or non-structural. All right, this one is block cracking. So I see some correct answers there. So block cracking, we know that we have to have a length of at least 45 feet of this established pattern to really identify that. You can't see that much in the picture, but it does continue on. But you see that kind of regular square looking, we've got those interconnected transverse and longitudinal cracks, but they are in a fairly regular pattern. So that's going to be block cracking. In terms of severity, we're going to need to look at the spalling. You can see right around this intersection in the middle of the picture, there's quite a bit of little pieces broken up there. So that's going to put us in that moderate to severe severity level. Density, can't see a whole lot of it, but if we saw this go on for a very long stretch of roadway, then we would put that in the high density. It continues to happen. And then in terms of structural, block cracking is not a structural issue in the beginning. However, if we don't do something to repair it, it can definitely become a structural problem. All right. That is all I have for the presentation today. We did finish up a little early, but I do have some final thoughts. If you have any other questions, put those in the questions pod. But one thing I do want to really reiterate is that collecting data is hugely important for being able to manage your overall pavement network. And the webinar that we will have next week will really expand on this. How do we take that information? How do we decide what to do? How do we fit it into our budget? And how do we make those decisions? So this, honestly, of the two, this one was the boring one, but It's the stuff that we need to know, because we've got to have the data to make those educated decisions. So this is how we get it. Now, do you need to do all of this for every single roadway in your entire network? Because that means somebody is going to have to go out with their measuring tape and their clipboard and take lots of notes. And a lot of us do not have the manpower available to take this on. It's almost a full-time job to keep up with it. If you look at all of it, every single mile of roadway in your network takes a very long time. By the time you finish it, it's time to start over and get another measure. But we do want to get some kind of a feel for how well our pavements are, how their lifespan is going. How fast are they deteriorating? When is that deterioration speeding up? What's typical? And then for your typical roadways, you know what to expect. You can start to set a little bit of idea of your timeline on when you need to budget X amount of money for this type of treatment option, or when you need to completely repave, when do you need to completely reconstruct. We would like to focus more on the preservation side of things, so there's less need for reconstruction, but we need to have an idea of how is this actually working with our pavements, and that helps us make better decisions financially. So I can't really stress enough how important it is that when you are putting a system like this together, it's easy to say, we got to do all of these things. We have to get all of this data. How much of that information will shape the decisions that you make? Do you need all of that data? If you start with something that's too intensive, too much data, and takes, only one person in your road department knows how to use it, and that person leaves, how are you going to maintain that? So I would encourage you to start with a system that you can maintain. Start with something that works. You can always grow it, but the worst thing that I've seen happen is when an agency decides we're going full bore into this, we get this huge system, and then they decide it's too much to keep up with, so they don't do it at all. I would rather see you do a visual survey and try to identify locations that have structural issues, and keep a log of that, and maybe nothing that's super formal. That would be better than kind of burning out and doing nothing at all. But keeping those records, being able to keep up with over time, how are these pavements lifespans going, that is going to be good information for being able to better use the budget that you have available. So that is kind of the precursor to what we will see next time. And so next Wednesday afternoon, we are going to talk about those budgets and strategies of how and when to fix things, and how to figure out where do I get the most bang for my buck. So next Wednesday, we'll have that. And I will leave this slide up for a few minutes. And if you have any questions, let me know. Feel free to email me. And if you do have a group attending with you today, be sure and send me the list of folks that we're sitting in. Make sure everyone gets a certificate. So with that, if there are no other questions, then I will sign off and let you guys enjoy the rest of your day. Thanks for attending.